Aim of the experiment. First, to determine the rate constant K at a fixed temperature, that is isothermal conditions. Second, to study the effect of temperature on K and to understand how temperature influences the rate of the reaction. Third, to determine the activation energy EA, which describes the energy required to initiate the reaction. This is the experimental setup of isothermal CSTR. Here, these are the reactor tanks which consist of sodium hydroxide and ethyl acetate. Here, these are the overhead tanks. These are the overhead tanks. We use overhead tanks to ensuring a constant feed rate. The overhead tank provides a steady and controlled flow of reactants to the CSTR due to its elevated position, which creates gravitational pressure. This ensures uniform feeding, crucial for maintaining consistent reaction kinetics and reliable experimental results, and also for maintaining a constant head pressure. These are the rotameters. Here we adjust the flow rate of the chemicals which flow into the CSTR, that is sodium hydroxide and ethyl acetate. This is the motherboard where we can set the point, and here this is the main switch. If you on, then the motor will be started, and these are the pumps. So pump 1 and pump 2 is for the sodium hydroxide and ethyl acetate. If you on, then the chemical flows into the CSTR, and this is the heater. Here we start the rotation of agitator. Here we are adjusting the speed to the 80 rpm. Temperature indicator where we can adjust the temperature, and here we on the agitator. This is a button where we start the agitator, and this is a CSTR. So the chemicals, the sodium hydroxide, ethyl acetate from the pipes will enter into the CSTR, and this is agitator uses for the uniform mixing of the chemical. From this pipe we collect the sample which is overflowed. So the sample is collected in the measuring cylinder for titrate.
Rotameter is a flow meter used to measure the flow rate of fluids, typically liquids or gases. It consists of a tapered tube and a float which moves up and down as we adjust the flow rate of the fluid using the knobs provided in the rotameter. The position of the float is proportional to the flow rate of fluid, which can be measured by the scale on the outside of the tube. When fluid flows through the rotameter, it enters the tapered tube at bottom and float rises with the increase in flow rate. The float reaches a point where buoyancy forces are equal to gravitational forces and it remains in equilibrium. The tapered tube is calibrated and the readings are taken from the scale provided on the outside of the tube. The scale has generally the units of volume per unit time. The advantages of rotameter are that rotameters are simple, low cost, they are easy to install and require no external power source. They are relatively unaffected by changes in temperature, pressure or viscosity.
A CSTR, a continuous stirred tank reactor, is a type of ideal chemical reactor where the contents are continuously stirred to ensure uniform composition throughout the reactor. It operates under steady state conditions where the reactants are fed into the reactor and the products are removed simultaneously. This ensures the composition inside the reactor remains the same as the composition in the exit stream. In this study, we focus on saponification reaction of ethyl acetate with sodium hydroxide. The objective is to determine the reaction rate constant K at a fixed temperature and to analyze how temperature influences the rate constant. It is a non-catalytic homogeneous reaction under isothermal conditions. The further allows us to calculate the activation energy for the reaction using the Arrhenius equation. Now let us see the reaction. NaOH plus CH3COOC2H5 give rise to CH3COONa plus C2H5OH. That is 1 mole of sodium hydroxide when reacted with 1 mole of ethyl acetate gives 1 mole of sodium acetate with 1 mole of ethyl alcohol. Now let us consider a reactor with a total volume of liquid inside the reactor VR, and the sum of the flow rates of the reactants entering the reactor is mu naught. So is the residence time, the average time a reactant molecule spends inside the reactor. It is calculated as τ is equals to reactor volume by volumetric feed rate. Now let us see the reaction kinetics of the saponification reaction. For saponification reaction, the second order nature arises because the rate depends on the concentration of both reactants, sodium hydroxide and ethyl acetate, CH3COOC2H5. Now let us consider the reaction A plus B give rise to C plus D. So the reaction rate minus RA would be equal to KCACB. Now if we assume the initial concentrations of A and B to be equal, that is CA0 is equals to CB0, the rate law simplifies as minus RA is equals to KCA square. Residence time plays a key role in achieving desired conversion levels. A higher residence time generally results in higher conversion, as the reactants have more time to react. For a second order reaction, the relationship between τ and the conversion is nonlinear. At the steady state condition, the performance equation for the reactor is given by τ is equals to CA0 XA by minus RA is equals to CA0 minus CA by minus RA. Where CA0 is the initial concentration of reactant, CA is the exit concentration of the reactant, XA is the degree of conversion, and minus RA is the rate of reaction. Now, substituting equation 1 in the equation 2, we get τ is equals to CA0 minus CA by K into CA square, which is equals to K equals CA0 minus CA by τ CA square. In this condition, we are assuming the initial concentration of both the reactants to be equal. By solving and rearranging the equation, we get tau is equals to 1 by k into Ca naught minus Ca by Ca square. Comparing this equation with the equation of a straight line, y is equals to mx passing through the origin, we get m is equals to 1 by k. By plotting the equation between tau and Ca naught minus Ca by Ca square, we get slope m is equals to 1 by k. This is the graphical method to find the value of rate constant. Now let's see the effect of temperature on the reaction rate. The temperature dependency of kinetic equation is given by Arrhenius' law. Arrhenius' law states that the rate of chemical reactions is affected by temperature. The law also states that particles must collide with enough energy and proper orientation for a reaction to occur. According to Arrhenius' law, K is equals to K naught into e power minus E by RT. Here, K naught is the frequency factor, E is the activation energy, R is the universal gas constant, and T is the absolute temperature. Applying log on both sides, we get ln K is equals to ln K naught minus E by RT. Here, E is the activation energy, R is the universal gas constant, and T is the temperature. Rearranging this equation, we get ln K is equals to minus E by R into 1 by T plus ln K naught. Now comparing this equation with the equation of a straight line, y is equals to mx plus c. Plot a graph of ln k versus 1 by k. By comparing both the equations, y is equals to ln k, 1 by t with x, we get a slope m is equals to minus e by r, and an intercept is equals to ln k naught. Here we find activation energy and K naught by the graphical method. To solve by analytical method, we can use formula ln k2 by k1 is equals to E by R into 1 by T1 minus 1 by T2. From this formula, we can find activation energy. And by formula K2 is equals to K naught e power minus E by RT, we can find the value of K naught analytical.
Before proceeding to the procedure, let us know the overview of the experiment. Let's know the aim of the experiment is to determine the rate constant K at a fixed temperature, that is at isothermal conditions, that study the effect of temperature on K to understand how the temperature influences the rate of reaction. Procedure involves three stages: pre-experimental setup, experimental procedure, post-experiment procedure. Pre-experimental setup. Prepare known molar concentration of sodium hydroxide and ethyl acetate in separate feed tanks and label the tanks clearly as A and B. Calibrate the flow meters. Check and calibrate the flow meters or rotometers for both reactant streams. Check the reactor. Ensure the reactor, stirrer and other equipment are clean and free from previous chemicals. Now the experimental procedure.
Now we are performing the isothermal CSTR experiment, and this is the setup of isothermal CSTR. And here we have two tanks. One is ethyl acetate and one is NaOH. And we are having overhead tanks to maintain the proper flow rate. And here we have two rotometers to maintain the flow rates. And we have a water bath and a reactor tank. And
First of all, prepare known molar concentration of sodium hydroxide and ethyl acetate in separate feed tanks, because precise concentrations ensure reproducibility of the experiment. For a second order reaction, both reactant concentrations significantly affect the reaction rate. Keeping them known and consistent allows for accurate calculations of the rate constant. And label the tanks clearly as A and B. Then switch on the main on the control panel and switch on the heater and adjust the temperature to 45 degrees Celsius by up and down buttons on the control panel. Here the green reading is the set temperature and the reading is the temperature that need to be attained. Then switch on the pump 1 and 2 buttons on the control panel. Now adjust the flow rate of the two streams at 10 lph using both the rotometer valves. Ensure the rotometers for each feed line are calibrated to deliver accurate flow rates, because the flow rates control the residence time, where is reactor volume and is total flow rate. Accurate flow rate control ensures proper mixing ratios and reproducibility. Use a water bath to maintain a constant temperature, because reaction rates are temperature dependent as described by the Arrhenius equation. Isothermal conditions ensure that temperature does not vary during the experiment, isolating the effects of other variables like residence time and flow rate. Now turn on the stirrer and set it to an appropriate speed for complete mixing. Once steady state temperature is achieved, wait for 10 minutes for sampling. Collect samples from the reactor outlet at regular intervals. Then take measuring cylinder and collect 20 ml of sample. Then we have to titrate it. Analyze the concentration of NaOH in the outlet samples using a titration method. Titrate with the standard acid like HCl to determine residual NaOH concentration.
This is the experimental setup for the titration of the sample. These two are the conical flask. Here it is a beaker which is filled with sodium hydroxide solution. These two are the measuring cylinders. In this we collect the sample and hydrochloric acid. This is a phenolphthalein indicator. Role of phenolphthalein indicator. Phenolphthalein is a common indicator used in titration. It changes color depending on the pH of the solution. Colorless in acidic solution where pH less than 8.2. Pink in slightly basic conditions where pH greater than 8.2. This is a burette filled with sodium hydroxide solution. In conical flask, we add sample and titrate it with sodium hydroxide solution, which is filled in burette. This is a sample filled in measuring cylinder till 20 ml. And we are taking another measuring cylinder. Here we are adding the hydrochloric acid 20 ml. And the HCl we are taking is a 0.1 normal HCl. This I'm taking 20 ml in measuring cylinder. Here, why we are adding HCl to the sample? To initiating the reaction. HCl might act as catalyst for the reaction being studied. Many chemical reactions, especially in aqueous solution, require acidic solution to proceed or to increase the reaction rate. For example, HCl can promote reactants, make them more reactive. And for maintaining pH control. Some reactions are highly pH sensitive and adding HCl ensures the solution stays within the desired acidic pH range. This is crucial in kinetic studies to isolate the effect of other variables and for adjusting ionic strength. In experiments involving ionic species, HCl can increase the ionic strength of the solution, which can influence reaction rates or solubility of the components. And for ensuring homogeneity, HCl might be used to dissolve reactants or intermediates, ensuring a uniform concentration throughout the reactor for consistent reaction monitoring. And for calibration or verification, in some cases, HCl addition could be a part of calibration or standardization step, helping to verify system parameters like flow rates, mixing efficiency, or reaction kinetics, etc. Generating byproducts. If the experiments involve reactions where the byproducts or intermediates need to be analyzed,
Adding this
may be
HCl
used
to the conical flask
or modulate secondary
immediately
reactions
after
for
taking the
these
sample.
studies. These are the reasons
And
we
now
are
this
adding
is a
HCl to
sample
the
of 20
sample.
ml adding to that same conical flask. This is a phenolphthalein indicator which I am adding 2 to 3 drops in the sample. Fill the burette with sodium hydroxide solution. Now I am filling the sodium hydroxide solution in the burette. Note the mark till 0 we had to fill. Now I am fix this burette to the burette stand and start titrating.
During the titration, NaOH neutralizes the acid in the sample, increasing the pH. At the equivalence point or slightly beyond, the pH of the solution shifts to the basic side. When the pH crosses the phenolphthalein transition range around 8.2 to 10, the indicator turns pink, signaling the endpoint of the titration. Here, why the sample is turning into pink color after titrating with the NaOH solution. In basic conditions, phenolphthalein molecules lose protons and form a pink colored anionic structure which absorbs light differently and appears pink to the eye.
Coming up next is the sample calculation. Taking one reading from the collected data set, we have the temperature as 38 degrees Celsius, burette reading as 8.6 ml, and the normality of the NaOH and HCl are provided to be 0.1 normal. We have set the flow rate to 10 lph using the rotameters provided in the apparatus. To find the normality of the reactant NaOH, we use the relation N1V1 equal to N2V2, wherein the first component is HCl and the second one being NaOH. After performing the calculations, we find the normality of NaOH to be 0.135, which attributes to the initial concentration of component A. The subsequent calculations give the value of Ca1 to be 0.057 mole per liter. Residence time is given by the ratio of the volume to the volumetric flow rate, which is found out to be 0.109 hours, which when converted to minutes is 6.54 minutes. The residence time is also given by the relation tau is equal to dCA by minus RA. Making the necessary substitutions in the equation, we find the value of the rate constant. This gives the theoretical value of rate constant, that is 3.67 liter per mole minute. Henceforth, we plot the graph between T and Ca0 minus Ca upon Ca square. The slope obtained from the graph gives the value of 1 by k, and thus the graphical value of rate constant is obtained. And then it is compared to the theoretical ones. The difference arises due to the non-ideality of the reactor. On the Arrhenius equation, we have the relation ln k is equal to minus E by R multiplied by 1 by T plus C, where E stands for the activation energy, R the gas constant, and T as the temperature. Next, we plot the graph between ln K and 1 by T. The slope obtained gives the value of minus E by R. Putting the value of R as 8.314, we find the activation energy. Taking a look at the graph for isothermal CSTR, we have the graph plotted between ln K and 1 by T. On the x-axis, we have plotted 1 by T, and on the y-axis, we have ln K. We mark all the obtained points on the graph and then join them together to form the curve. Taking any 2 points on the graph, we find the slope by the formula m is equal to y2 minus y1 by x2 minus x1, which corresponds to the value of minus E by R, where E is the activation energy and R stands for the gas constant. Precautions that are need to be taken while performing the experiment are as follows. Measure the exact volume of water and weigh the chemicals. Always use clean water and good quality chemicals and standard solution for titration. Use electronic balance for weighing of chemicals. Don't mix the droppers of different chemicals. Keep close all the drain valves and vent valves should be open while filling the reactant in feed tanks. Flow should not be disturbed during experiment. Handle the chemicals carefully. There should be no air in the flow during experiment.
Closing procedure. We had to switch off all the main of the apparatus after the completion of the experiment, where we are offing the pump 1 and pump 2 to stop the flow of the chemical. We have to off the heater. So when we off the pump, the flow of chemicals into the CSTR will be stopped. And wash all the glassware items after finishing the experiment. And here, this is a chemical which we are titrated, so we had to rinse it and wash properly. We had to pour the chemical which is left, that is sodium hydroxide, into the beaker. Submit all the glassware.